Hello, my name is Jack Barrich, and this is Ocean Solutions, a podcast produced by Altasea at the Port of Los Angeles. Altasea is developing the most innovative ocean research campus in the world, a place where scientists, educators, and business people can work together on solving some of mankind's most pressing challenges, including climate change, energy supply, and global food security. On today's show are Regina Wetzer and Dean Penchev, scientists from the LA Museum of Natural History. Regina and Dean are on a team that studies marine biodiversity in the ocean waters of Los Angeles. From whales to algae and everything in between, they talk about a new technique where a cup of seawater can identify the DNA of all the species from the surrounding area of where it was taken. This is really fascinating stuff, and I hope you enjoy the show. Hey, Regina. Hey, Dean. Thank you guys for joining us today.
It's our pleasure.
Yep. So you guys run a thing at the LA Museum of Natural History called Disco. That sounds really Saturday Night Feverish.
It does.
What is it exactly? I'm sure John Travolta doesn't come dancing through your guys' work. What does Disco stand for?
It stands for the Diversity Initiative for the Southern California Ocean.
And what does that mean?
We are looking at the biodiversity of the ocean that's right out our door in front of Los Angeles and around the South Bay.
So when you say biodiversity, what does that exactly mean? Biodiversity, is it seaweed? Is it coral? Is it animal? Like, what does that exactly mean?
It's all of those things.
Right.
We don't have too many coral species, but we have all kinds of algae. We have everything from whales to toxic algae to sponges and worms and crabs and fish and everything in between. So it's that entire diversity, just as we have on land, occurs in the ocean.
Sure.
And we are studying the ocean.
Right.
It's a little bit more difficult because it's covered with water. So
right.
A couple of other techniques need to be employed.
Yeah. Now, I understand that the current monitoring technology doesn't really keep pace with the changes in the ocean. What are you guys doing that allows scientists to better track what's happening in the ocean? You know, what is it that, what have you created, or maybe not just you guys specifically, but what has been created to make this a more efficient process?
So that's the part that we're working on very hard with some of our academic colleagues. Traditionally, nets, seines, all kinds of capture devices would be used. You would have specialized trained personnel that can do these identifications and counts and assessments. And the technology is now such that we can actually reach out and just take a sample of seawater, for example. Mm-hmm. And since everything sheds DNA in the environment, as we walk around on land, we shed DNA.
Right.
All these organisms are doing the same, such that we can actually filter that seawater onto a filter, capture that DNA, and then analyze and look at who has been there and is there now.
Oh, I got it. Well, I think I got it. So you capture this little cup. Is it a big cup or a little cup?
It can be like your coffee cup.
Oh, okay. So coffee cup. And so all of the living organisms that were in the vicinity of that water their DNA will be in that water?
Will be captured in that water.
Wow. And it's super efficient. It sounds like you don't miss anything?
Well,
Dean's laughing, so maybe we do. Or do we not? I don't know.
So, yeah, I mean, this is a technology that is absolutely going to be used, and it is in the becoming stage right now. So the reason I'm laughing is we're in the midst right now of analyzing a bunch of data that we've collected from waters off the port and the areas right here. And this is a very well-studied area. So there are certainly species that we know should be here and we know are here from other reasons. Some of those don't show up in our genetic data. Now, there are lots and lots of reasons for that. We may not have the right genetic sensors to pick up those particular species. There may not have been any around that day.
Yeah, they were just going for a swim somewhere else.
They were just elsewhere, and so we're not close enough to be in the cloud of their DNA.
And I'm going to interrupt you. So if, I was being kind of facetious about they were all swimming somewhere else, but like as an example of a whale, if you were out there tracking it in the traditional way, they wouldn't have been there either, right? So the same, you wouldn't have seen it on the day you were tracking because it was not there that day. Same thing with this.
Bingo. That's exactly right. Every type of sampling that you do has some kind of blind spots or biases. As, the seines that we pull behind a boat to do the fish trawl is not going to pick up a whale.
Right.
It's just not going, and that doesn't surprise us. It's not like, oh my God, we missed the whale. We expect that. That's perfectly reasonable. With the eDNA, there are going to be blind spots like that. And that's the reason why it's not quite ready for prime time yet. We are exploring what are the blind spots and what are the good spots.
Right.
For example, when we were looking at the water in the ports, we did find DNA from all of the fish species that we expected to find from the trawls that were done at the same time. We found 155 other fish species.
I was just going to ask you, did you guys find things you were surprised to find that you didn't expect to find? Do you ever go, wow, I didn't know that was down there?
Absolutely, yes. And that's what's totally cool about this. And again, it produces so much information that culling through that and organizing that and validating that is taking a lot more effort than any of us had anticipated.
Sure, because you're finding more than you expected to find?
Correct.
It's exciting. You know, it's funny. It just like opens my mind up because when I think of ocean exploration, using my, 20th century very linear mind, I think of something you actually see with your eyes. You go, oh, look, there is a crab and there's crabs down here. But you guys, because of this, you can actually track things that you can't even see.
Correct, because the crab has a pelagic larvae, a larvae that is in the water column, so it would be very, very small, would use a very different sampling technique of a specialized plankton net to be able to be captured, rather than a bottom trawl that would capture a crab. So we would pick up crab DNA, and it could be a larvae that's swimming in the water column that would not have necessarily been expected.
And is that why you ascertained that maybe you found things down there that you weren't expecting to because you physically in the past wouldn't have been able to see it?
That's correct. It can also be things that are super rare or things that are really good at avoiding the net for some reason. So maybe a fish species is just really good at avoiding the net.
So kind of like a shifty guy who the cops are after they can never catch.
And some of the larvae will have large population sizes at specific points, and then they may settle down into the ground, into the benthos, and be stable there, and we would pick them up differentially.
Wow. So after you do this monitoring, how do you share your findings with the marine biologists and other people in the scientific community? Are you creating a database or anything that they can tap into?
Yes. That's one of the things that we emphasize very strongly in the museum is all of the data that we produce is publicly available as fast as we can get it out into public access. It's not available the day we collect it because we don't even have access to it yet at that point. So it takes a while to get it out. But there are existing databases for this kind of genetic data. The best known one is probably GenBank, and that's a repository for all kinds of different genetic information. There is a specialized database for the genetic information that's used for this kind of species ID kind of work, which is generally called genetic barcoding, by analogy to a barcode in a supermarket where you can kind of blip something and get an ID. These genetic barcodes are so-called, have a specialized database, and we post it directly to that. So everything we get goes to those databases. We get access, and everyone else gets access to those databases, but our data are immediately publicly accessible.
So, okay, so you guys go out there, you track it, you find it, you put it in a database. These scientists have access to it. But why is it important to study this marine biodiversity on nearshore waters that you guys do? Are there solutions to mankind's challenges that can come from these studies? What is it that, for the average guy like myself, what am I going to say? Why would you say to me this is important?
So we all know excruciatingly well at this point that the world is changing.
Sure.
Our climate is changing, and that includes the oceans. The oceans are changing.
Right.
As Regina said, it's really hard for us to see how that's affecting ocean life, much harder than on land, to see how climate change is affecting things on land. What's happening right now is the rate at which the ocean is changing is accelerating. It's getting faster and faster as temperature is changing. And yet we are still using monitoring methods that are incredibly expensive, take incredible amounts of expertise, and are just too darn slow to track the changes.
Got it.
If we are going to manage these changes, and when I say manage, things like where are we going to put protected areas? Where are we going to allow fishing? Where are we going to cut back on fishing? Where are we going to do these kinds of management things? we need to know the first and most basic thing is who is where.
Right.
And we are lagging way behind on the technology right now to be able to do that using the traditional methods. It's too expensive, takes too much boat time, takes too much personnel time. This is a way to shortcut that process by being able to take a water sample, inventory who's there. It's much cheaper, much faster, and much more effective.
I understand. So like you had mentioned, one of the examples is a fishery. So it could be that it's becoming depleted and you know that if you don't do something about it, there will no longer be fish there. And now you'll have the ability to, more in real time, make those assessments. And so we don't overfish or do some of the other things that might be harmful. Is that like one real good example?
Yes.
That's a real good example in the terms of the fish are there because there's a food source for them there. Mm-hmm. If the food source is being affected by the waters becoming more acidic or the temperature changes that they cannot tolerate, those fish are trying to move someplace else. Right. We're already seeing some of these effects of food sources probably affecting some of the marine mammals that are now looking vanished and hungry because they're not getting what they need.
Got it.
Other things are going to become more abundant. Things are also moving northward at a pretty good rate, just like national parks are made like you have Yellowstone and you have the organisms in it, and the park boundaries are not moving, but the organisms are moving further north as they are adapting to their changing habitats. The same thing happens on our coast.
Got it. So I had previously interviewed, it's been a while, Dr. Dan Pondella from the Southern California Marine Institute, and he was working on a project that was restoring coral reefs. And the idea of that was that, you know, by restoring the health of that reef, you bring back the fishery, because now the fish can survive and can, you know, have the food and the ecosystem that it needs. Is that also like maybe one of the things we talk about fishing, stop fishing because the fish it's overfished, but the other thing is if you can put the food back in and you know that it's missing and you go, hey, if we can fix this, the fishery will return. Would that be the other side of that sort of example? That
absolutely is. And there is good evidence now that, for example, one way of enhancing fisheries, besides regulating and limiting the catch, is to make preserve areas.
Right.
And preserves can be at various levels and various kinds. Preserve areas allow fish to reproduce in a way that if they are subject to fishing, they cannot. And so there's good evidence that that actually does work well for fisheries. However, good evidence is maybe not good enough. One of the collaborators we're working with very directly in this project is a graduate student at UCLA called Zach Gold. Mm-hmm. And his thesis project is to develop the use of this environmental DNA as a tool to sample seawater inside and outside of marine protected areas to look to see what is the signal of having a marine protected area. Can you tell that the marine protected area is changing fish densities by its very presence, by its protection? So therefore, is it enhancing the fisheries nearby?
Right.
And that's just a tremendously exciting tool to be able to apply to look at how and whether we are augmenting fisheries with various conservation technologies.
So bringing it back to like the challenges that we're trying to face here, you know, AltaSea's, one of the three things that we talk about the most are energy supply, climate change, and global food security. So it sounds like this, what we've been talking about, falls right into the category of global food security, right? So if we can keep a healthier ocean and figure out what is missing and what is needed to be fixed, then we also can create more food, and you know, because we are going to need to have to figure that out as the population grows and our ability to grow food on the earth itself, you know, diminishes.
Yeah, there's a huge global demand, increasing global demand for protein, and it's going to come from the ocean, because we can't get much more from the land.
So one of the characteristic organisms on our shores here, just beyond the port and behind the peninsula, are the extensive kelp forests.
Right.
And it turns out that the large, gigantic kelp, the Macrocystis, is also genetically most diverse right here on the backside of Palos Verdes. Huh. So we are working with colleagues, again, to look at what those genetic markers are that allow for this diversity, which of these organisms have a potential, the analogy to the coral work that's being done, to make stocks that are more resilient to changing environmental conditions.
Yeah, that's exciting stuff. Well, listen, unfortunately we're running out of time, so I'm just going to have to say thank you for coming, but really, really good stuff. I really enjoyed this conversation. Thank you.
Our pleasure.
Jack.
Thank you. Thank you for listening to Ocean Solutions, produced by AltaSea at the Port of Los Angeles. To learn more about AltaSea, please visit altasea.org.